Okay, so let's see. Today's video and assignment is kind of just a follow-up from the first assignment on the volume of revolution. So if you look at the handout or assignment, it's split up really into three sections. You've got a disk section, a washer section, and then on the back, I didn't title this section, and we'll have a follow-up for this as well. We'll have another handout that goes over this last section, which is a little bit tricky. Okay, so this today is really, today's assignment, the second assignment, is just to do the disk and washer portions of this handout, and we'll save that last part for another time. Okay, the disk problems on here are really pretty straightforward. I don't think there's a whole lot more to say about these, and so what I want to do is focus on the washer problems in this section. And so I'm going to do problems, let's see here, 6, 8, and 10. And these are all, I think, good washer problems and good practice for this topic. So let's take a look at these. Let's see here. Problem 6 says we want to find the volume of revolution for y equals square root x, let's see, and y equals x cubed, or really the area between them. Okay. So there's our two functions, and as always, I think it's a good idea to draw a sketch of this so that we know what we're working with. And again, I encourage you to use your graphing calculator. If you're not sure what these are going to be looking like, then that can be helpful to you. So the square root x function is going to be doing something like this. So we'll label that. And then the y equals x cubed function comes through and does something like that. Oh, and I almost forgot, in problem 6, we're going around or about the x-axis, and that's important. Okay, so again, let's identify the piece of area that we want to rotate. That's another really vital aspect to doing these problems. So identify that piece of area that's going to get rotated, okay? And then, as I always try to do, I'll erase it again so that we don't clutter up the diagram. Okay, now to draw the rotation of this around the x-axis, what I normally do is just draw a little sort of mirror image over on the other side. That's not a great depiction of what's going on, but I never claim to be a great artist. So then we draw our cross section, and this is a washer. Okay, notice, and I'll try to point this out as we do these washer problems. Our axis of rotation is the x-axis. If that area that you're rotating is not flush up against your axis of rotation, it will be a washer problem. Okay, I'll talk more about that as we do more of these problems, but that's an important thing to recognize and to determine whether or not you're doing a disk or a washer. So there's the thickness of that interior section. Here's the thickness for the whole washer. And again, those thicknesses are delta x's because we're rotating around the x-axis and we're going to be integrating with respect to x. Okay, so for this washer problem, remember that our volume is going to be pi integral big R squared minus little r squared, and then dx if we're going around the x-axis, and dy if we're going around the y-axis. So let's identify our radii here, the big R and the little r. Well, the little r is right in there, and that's this function, the x cubed function. Our big R extends all the way to the edge, and that's our square root function. Okay, so this formula then will be pi. Big R is the square root x function, all squared. And then the little r is the x cubed function, all squared. Oh, and I don't have our limits of integration in there. We're going from 0 out to whichever this point is right here. You can find that on the calculator, although by inspection, I think that this is just going to be 1, right? That's where these are going to intersect, is where x is equal to 1, and y is equal to 1 as well at that point. Okay, so now we've got everything set up. So let's do a little bit of algebra before we do the integration here. Square root of x squared will just be x to the first power. X cubed squared will be x to the 6th. And if you've forgotten some of your rules of exponents, please do refresh your memory. I hate to see people make mistakes in this part of the problem rather than the calculus part. Okay, so let's do the integration. This will be x squared over 2 minus x to the 7th over 7 from 0 to 1. So if we plug those values in, we'll get a half minus a 7th, and then minus 0. And you can evaluate this on the calculator if you'd like to, but we're going to have a common denominator of 14. This will be 7/14 minus 2/14. And so that should be 5 pi over 14, or some equivalent version of that. I've tried to program all of the quizzes that you're going to be doing online so that it'll accept 5 pi over 14, it'll accept some decimal multiple of pi, or some approximation of this irrational value. Those should all be handled pretty well by those online quizzes. Okay, so that's problem 6. We come out of this with 5 pi over 14. Let's take a look at problem 8. Let's see, we'll leave that formula there. Okay, problem 8, we've got x equals y cubed, x equal to 8, and y equal to 0, and here we're going about the y-axis. Okay, so let's make a little sketch for ourselves here. X equals y cubed, right? If we turn this around so that your graphing calculator can handle it, that would be y equals cube root x, and that's going to come out looking something like this. X equals 8, you know, is a vertical line where x is equal to 8. Let's see, this is x equals y cubed. And then what else? Y equals 0. So that's down here. So that identifies the area that we want to rotate, right? I'll shade this in a little bit and then go back and erase it. But that's the piece of area that we now want to rotate around the y-axis. Okay, so let's clean this up a little bit so that we don't clutter the diagram. And again, if I want to try to draw this, I'm going to make a little mirror image over here, and then our cross section will be like this. And again, notice our axis of rotation is here, and our area is not flush up against it. That's what creates the hole when we do that rotation. Here's the outer edge of that washer, right? There's the thickness. And again, notice that thickness is a delta y. That thickness is along the y-axis, and that tells us that when we do our integration for this problem, we want functions of y, which we already have here, okay? And we're going to integrate with respect to y. We've got our inner piece of the washer has a thickness along the y-axis as well. Okay, so now we want to identify our big R and little r in this problem. Here's the little r right here. And then the big R extends all the way to the edge. Okay? Now notice that this big R doesn't change as you go from the bottom to the top. It's always going to be equal to 8. So that's not even a function. It's, well, if you want to consider it a constant function, that's fine, okay? But it is constant. It's not changing. This little r, though, is changing, okay? And this is always the x value, and this is telling us right here that x value is always equal to a function of y, which is y cubed. Okay, so here's our big R, here's our little r. Now we can set up our integral. We'll have pi, the big R is 8, the little r is y cubed. Those both need to get squared. We're integrating with respect to y, so we've got a dy there. And now we just need to figure out what are our limits of integration. We're starting down here at y equals 0. And remember, if this is a dy and these are functions of y, these limits of integration have to be y values. So down here where y is 0, that's where we're starting. And we're going up to this point right here, which is where y is equal to 2. So we're integrating from 0 up to 2. Okay, so let's go in and do a little bit of algebra here. 0 to 2, 64 minus y to the 6th dy. So there's our integral. And so this will be 64y minus y to the 7th over 7 from 0 to 2. So that'll be 128 minus 128 over 7, and then minus 0. And let's see, what does that calculate out to? That comes out to be 768 pi over 7. And again, you can go ahead and do this division and express this as a multiple of pi, a decimal multiple of pi, or you can approximate that irrational value, and those answers are all acceptable. Okay, so there's problem 8. Let's look at one more of these, problem 10. Okay, let's see. Problem 10, we are working with y equals 2x, y equals x, and y equals 6. But here's the important part. We're going about the y-axis. So I'll talk about that more in a minute. But let's get these things graphed. So y equals 2x is going to be kind of steep right here. And then the y equals x is a lot less steep. And then y equals 6, right, is that horizontal line where y is equal to 6. So there's our area right there. Again, right, this is an important thing to do, is identify the piece of area that's getting rotated, in this case, around the y-axis. Okay, so let me erase this now and then try to draw what's happening here. So let's make a little mirror image over here. And again, notice that that area that we identified is not flush up against the axis of rotation. That's what creates the hole. Here's the cross section with our washer. There's the thickness of that washer along the y-axis, right? Notice that that's a delta y. And then we've got a thickness in there as well. Okay? So what does this thing look like? It's kind of interesting sometimes to think about it, is that you'll have this set up like this, and then it'll come down to a point like that. So all our volume is going to be in here, and you've got that empty stuff in the middle of it. Okay, so now what? Well, since this is going around the y-axis, these need to be expressed as functions of y, or they need to be put into the form x equals. This is pretty straightforward. Here, x is equal to y over 2. This one, x equals y, y equals x, is all kind of the same thing. Okay? All right, so now let's go in and identify our radii. Here's the little r right here, and then the big R is if we extend it all the way to the edge. Okay? So in this case, the big R comes to our y equals x function, and so the function of y that we want is just x equals 1y. Over here, the little r, the function of y that we want is this one right here, x equals y over 2. All right, so now we're all set up to do the integral. So we want this to be pi, and then the big R is y squared, and then the little r is y over 2 squared. And again, we're integrating with respect to y, and so we need our limits of integration to be values of y. We're starting down here at y equals 0, and we're going up to y equals 6. So there's that. Now we've got pi, integral from 0 to 6. This will be y squared minus y squared over 4. And let's take this one more step to make it just that much easier to work with, right? 1y squared minus a fourth y squared leaves us with 3/4 y squared. So then when we integrate, we'll have the pi here. So this will be y cubed over 3. These 3's will cancel. And so that'll be 1/4 y cubed, integral from 0 to 6. And so let's see here. This is pi 1/4 times 216, that's 6 to the 3rd power, minus 0. And so what do we get out of that? 54 pi. Okay, so like I said, today's assignment is really just a follow-up on that initial assignment on the volume of revolution. I wanted to take a little bit more time to look at these washer problems again. Identifying the big R and the little r can be a little bit tricky. Getting used to going around the y-axis with the functions of y can be a little bit tricky. So that's it for today. We will look at the back page of this handout in the next video. And then after that, there'll actually be another handout on that same topic. So we will get to those this week, and I'll post those as soon as I can. Thanks.